Hello. I'm going to talk a little bit about the Portfolio Percentile Premium Principle. And the reason I'm doing this is that I think in class I went ahead and sort of rushed through this is how I calculate it without going over in enough detail the justification of why you do it and how it works. So without further ado, let's go ahead and get started. And we'll go ahead and start with this. So this is the idea. The random variable in question I'm going to talk about will be the loss random variable. And we'll be doing with net loss, meaning expenses are not considered. Yeah, that's just for simplicity. I want to keep as many things down here. And this in particular, by L, I will mean by traditionally LN0, that is the present value of the net loss variable. And by L bar, I will mean a sum of, let's say, I equals 1. Now, this is a different n than this one, where Li are the loss variables for n independent identical policies. Now, of course, these are all important things. Independent, for example, of all the people are going to live in something where there's a big tragedy or a pandemic outbreak, as we've seen, that some of these assumptions fall by the wayside. But for the purposes of the discussion, we will assume that these are in fact independent variables, and this is a mean or an average of them. And remember how L is defined, or each one of these LIs. It will be the present value of outgo, that is the benefit, what the policy pays, minus the present value of the premiums. Okay. And ideal, if a loss is positive, it means the company loses money. For example, you issue a policy and then the unfortunate person dies right after the first premium. That's definitely a loss. That's a positive loss. And our goal is to, in this case, find a premium. In fact, let me retreat here. I really got ahead of myself a little bit, got a little sloppy. Our goal, well, even before I even say our goal, I really got a little bit sloppy here. I should have explained this a little better. But typically, the loss here will be the present value of the benefit minus the present value of benefit B, our premiums paid. I know I already wrote that down, but I want to make that clear. But these are present values. And our goal is to, and this will be indicate the benefit for each policy, and premium will indicate the premium for each policy, is to find, given the benefit B, find P so that the probability of the average of this portfolio, the probability of this average of these loss variables being negative is sufficiently high. And this could be things like 0.01, 0.025, 0.05, etc. Whatever the assumed risk is. So the idea is that we want to find the probability that our loss variable is going to be negative, the average of the loss. We want that to be sufficiently high. Now, the problem here is that the distributions for these variables here can be kind of gnarly, but we do have a central limit there. Which assumes that if you have these independent random variables and you take their average, that if you take the random variable x bar minus mu, the mean, divided by sigma over the square root of n, this approaches standard normal as n goes to infinity. Now I know the joke is that n equals 30 is infinity, but we're gonna be working with numbers much higher than that. So the idea here is that if we can do something to get this to be normal, then we can use z less than z alpha equals 1 minus alpha. So we can somehow do that. So how can we get this to look like this and keep it algebraically the same? And let's start. Let's start here. So let's do this. We have now our L bar, and we now have our 0. Now what I'm going to do by different colors is I'll just go ahead and start doing this. I can now take away the mu from both sides, right? And then I can then divide both sides by, let's do it with red here. Divide by both sides by this, the square root of sigma over the square root of, sigma over the square root of n. And then we know that this is going to be 1 minus alpha. So we've transformed this. This is now, we can now use the normal distribution. And we could set minus mu over sigma over the square root of n to be z alpha. See? That's a good place to be. So the next thing we have to do, so our next step given that our next step, we talk about mu and sigma and the square root of n. Okay, let's do that. Now for our mu, this would be the expectation of the standard loss variable. And you can do this one of two ways. You can either go to expectations right away and use the tables, or you could use the expectation of the inflow, which would be the benefit paid off. And I'm using the end of the year of death, so that's curtate life plus 1. And there's discount factor. Subtract the premiums, and this is the annuity due. 1 minus this. Curtate life divided by discount. Right? And this, of course, doing a little bit of algebra, it's the expectation of B plus P over D. And then minus P over D. And then by using the expectation of a constant times a random variable is just going to be that. So we end up with B plus P over D The expectation of this is just that. And that's the top right there. Now, the next thing we want to do is we want to move this, the square root of n to in the denominator to the numerator. So, well, we're not quite ready to do that yet. So that's the first part. Now, the second part is the denominator. And we know our sigma is going to be the square root of the variance. And that's going to be the square root. I mean, that's going to be the, in this case, the square root of the variance of, now we have a random variable right here. Try to get my this. And extend the square root. But then we know that the variance of ax plus b is a squared variance of x. So this is going to be b plus premium divided by discount squared variance of this random variable, all square rooted. But, and then of course this doesn't affect the variance because it's just a shift. Well, you take the square root of that, you get this. And then the square root of this, well, we have the variance for, we have symbols for that. So that gives you the denominator, right? So that's our first step right here. So let's just do this and just replace what I have here. Let's go to a new one. So, okay, so now we're cooking. So what we have right here now, so we now have this mu over, well, I know it's technically, I still have it as minus mu over the sigma over the square root of n is equal to square root of n mu over sigma. But in the very top, we have benefit plus premium divided by discount. In this case, we have that. And this is all divided by and we've had this set to, in this case, z alpha, right? So we now have that. And then multiplying both sides by -1, we get what we had in class. Is going to equal minus z alpha multiplied by this right here. Now, in principle, you have you can combine these to get one factor of p on this side for premium. You can combine this to get another factor of p in this. So in fact, you have a linear equation, well, sort of linear, an affine equation involving p and a another number. And solve that, and that will be the solution for the portfolio premium percentile principle. Okay, so now let's go ahead and use an example. So in the example I want to use, And I believe I have the parameters here, and I did a lot of the work already done. So let's say the life aged X is 50, standard ultimate. Interest rate is 5%. Paid into year of death. Premiums, annuity due, annual. Okay, so pretty standard, straightforward. And let's say the benefit that I have worked out here is $200,000. So working this out, looking this up at the table, 0.18931, set double the force of interest is 0.05108. This thing here, which appears on the side, turns out to be 0.123457377. That's all kind of routine. And let's say we're interested in alpha equaling 0.05. So Z alpha is 1.96. Nah, I screwed that up, 1.645. Almost got two wrote. Single tail, right? Single tail. So our equation here, this equation that we have up there, and let's say our n is 100 squared. So the actual equation we have only on discount, 1 minus 1 over 1.05, okay? So when we got all this, and then of course 1 over discount is 21. So now let's go ahead and take this that didn't work too well. Let's do this again. Copy and paste it down here. So let's go ahead and plug in everything. So now plugging in everything. Square root of n is 100. The benefit is 200,000. P over D is 21p. And we have this, reading this off the table, 18931 minus 21p is equal to minus 1.645, 200,000 plus 21p multiplied by all that square root. And grinding through the numbers, what we end up getting is the top when you combine these. Now remember, you're combining p here and you're combining p here. We get 3786,200 minus 1702.449 premium is going to equal minus 40617.47703 minus 4.264835,088p. Now notice this is going to be somewhat minuscule compared to this, and this is also going to be smaller. So now it's a fairly routine thing to do while the algebra and solve. And so combining on both sides, what we end up with, adding and subtracting, this is pretty routine now. Watch me screw it up. Equals 1.6. I mean, screw that up. Told you I would. Come on. All right. 1.698. 184,165p. And doing the solution, we get P is equal to $2,253.48 a year. Right? Now note, so that solves this. Now I want to notice this. Note, by the equivalence principle, which seeks to set the expectation of this equal to 0, the equation we'd actually have is the benefit, 200,000 times 0.18931 equals the premium times 17.0245. Now, if that went a little quickly, I should explain where that came from. This is a benefit. This is a 50. And this is a present value, expected present value for annuity due. This equation is this equation. Well, this thing here, which I'll call by the equivalence principle, is 2223.97, which is less. And that's to be expected. The equivalence principle, in fact, is going to be less than the portfolio percentile principle premium. Now, why is that? Well, you can probably see why, but I'll go through a very quick derivation, so hopefully this makes sense. So Y is P equivalence less than going to be less than or equal to the portfolio percentile principle. Well, let's just take a look here. If we get right down to it, the thing is that it is predicated on solving this. The square root of n over sigma is negative z alpha, right? Now, this mu right here, if you think about it, all this mu is, this is going to be the benefit. Screw that up a little bit. This mu, even though I developed this from the random variable principle, this is really the expectation. So mu is just the expectation of the loss variable. Well, the quick way to cancel to do that will be the benefit, and I'm using into your life, so it's going to be this minus p this. That's going to be the numerator, right? And this sigma, I'll just go ahead and leave write it this way. And of course, the square root of, didn't leave myself enough room. Better do that. Better leave myself enough room. The variance of the random variable. And this is going to be equal to minus z alpha. Then if you just move all this to the other side, we get v ax minus p. Now I want to write this way. I want to leave this as a factor. Now we're dividing by the square root of n. And then we have this. Then we have the standard deviation. Now let's take a look at these factors separately, because this is really what this boils down to for this simple case. Now, the reason it's usually not taught this way, at least not all the time, is that the left-hand side can be more complicated when you start bringing in expenses or things like that. But we have this basic equation here. Now notice, the first thing to notice, as n goes to infinity, the right-hand side, the right-hand side goes to 0. So it turns out that P approaches the equivalence principle, P, because the right-hand side going closer to 0, eventually 0, means you're just doing the equivalence principle right away. So if you take this over a bunch of policies, that happens. The second thing, as far as the Z alpha, well, then this really, you're talking about a single policy. And there you go, same sort of thing right here. And the third thing that you have, and this is the third feature, which I didn't really stress in class right here, but 3, the variance of the random variable, if this goes to 0, same sort of thing. You have less variance in policies. Now that makes total sense, I think. So you can look now, this part right here, there's really, this is fixed, and this is what you're solving for, the P right here. So that's not really, you can do too much with. But, and this of course is a feature of the policy issued. So where the variation comes less, let's say the extreme, that's sort of the extremes, a smaller variation means that the portfolio percentile principle premium is going to be very close to the equivalence equivalence principle premium. But the real one, big one here is right here is this N. So that's what's going on with that. So I think I've talked enough. So I'll stop the share, and thanks for watching.